Welcome to Math341, lecture 14. So what I want to do today is talk a little bit more about expectation, more consequences of linearity of expectation. No one asked me to do specific problems from the exam or to do other practice problems or to do coding. If you guys want to see more of that in class, let me know. I have the lectures from the last time I taught this class online. It's very easy to say, we're not going to do this part, and we're going to free up that class time to do something else. So this is your chance to adjust a little bit of what we're going to do. I'm going to try to do a little bit less detail than last time, because we've already done a little bit of some of the theorems. So the big stuff is linearity of expectation. And then we will see today the beginning of how useful this is. And then as the semester progresses, we will see some tremendous applications of this. So we have the following. I'll call it a lemma. If y equals ax plus b, then the expected value of y is a expected value of x plus b. We essentially proved this last time when we had, a1 g1 of x1 plus a2 g2 of x2. All you do now is you take g1 of x1 to be x1, and you take g2 of x2 to be the constant b. So we've really already shown this. The big one, we'll call it a theorem. If x and y are independent, then this implies the expected value of the product is the product of the expected values. So this is a terrific result. It means we can reduce the calculation of compound objects to simple objects. So before proving, it's always a good idea to get a sense of, do we need this assumption? Is this assumption for convenience, or is this assumption fundamental? When we looked at linearity of expectation, we could have proved that the expected value of a sum is the sum of the expected values if independent, but we actually don't need to use independence in the proof. So can somebody give me two random variables that are not independent? And I want to be able to calculate their product nicely. Yes?
I was going to say something about the runs scored and the runs allowed.
Yeah, but that's going to be a long calculation. I don't want to work. Yes?
Probability of drawing a red card versus probability of drawing a heart.
Okay. So that's a little bit more long and involved.
That's long and involved?
It's a little bit long and involved. X, which will my other variable be? Yes?
First is sorry, what was the first variable now?
First variable is x.
X, y.
What should y be?
X again.
So what possibilities? Look at x and x. Look at the same thing. Okay? And then you would have the expected value of xx is the expected value of x squared minus the expected value of x squared. So if they were independent, we know this would be true, and we would have 0. So the question now is, if this held for all random variables, not just independent ones, what should this equal? What should this equal? Again, this theorem requires x and y to be independent. What should this be? It should be well, we're assuming we want to show that this result does not necessarily hold if x and y are not independent. If it's still held, what would this result have to equal?
X squared.
Right, and so what would this expression simplify to? This would then become ex minus ex. This would simplify to 0. So all you have to do is find any random variable whose variance is not 0, and you have a contradiction. Okay? Yes?
I think you meant to write the square inside.
Oh, sorry. Thank you. Yes, I did mean to have the square inside. Thank you. So all you need to do is find one random variable that has a positive variance, and you're done. And you see that the assumption of independence is essential. Another thing you could look at is x and 1 over x, so assume your random variable is non-zero, then the expected value of x, 1 over x, is just 1. And does that equal the expected value of x times the expected value of 1 over x? So by choosing nice y's in terms of x's, you can often make it very easy to test and see how essential is this hypothesis. And we see that if we drop the independence, we do not expect that this holds in general. We do not expect that the expected value of a product is the product of the expected values. This is fundamentally requiring independence. This is why variance calculations are so much harder than mean calculations. For the mean, that's just the expected value of something that's nice. Expected value of a sum is the sum of the expected values. For variance, you're going to have a quadratic. You're going to have squared terms. This leads to the correlations, the covariances. Much, much worse. All right. So we want to prove that if independent, the expected value of a product is the product of the expected values. All right, so proof. All right. So the question is, how do we want to prove something like this? We have lots of different ways we can look at it. Right? We have a joint probability density function. And what do we know about the joint density function if they're independent? So, yes?
The product of the probability.
Yeah, it's the product of the marginals. You know, things are going to factor. And so if we want to calculate, if we let z equal xy, and we want to calculate the expected value of z, this is going to lead to the following calculation. The integral x goes from minus infinity to infinity, integral y goes from minus infinity to infinity, xy fx of x, fy of y, dy dx. And now, because things split, we can now just write this as the expected value of x times the expected value of y. And that will essentially be the proof here. You can make it a little bit more rigorous and go into a little bit more detail, but I think this is enough. Okay, so related to this is the following case. Let's say x and y are independent. The expected value of x minus mu x times y minus mu y. What should this equal? Yes? So this is the covariance of x and y. What should that equal for this problem? It should be 0. So there's a couple of ways to do this. So the first proof is algebra. Roll up your sleeves. First, outside, inside, last, expand everything out. Mu x and mu y, they're constants. So you can take them outside the expectation. And when the dust settles, everything will cancel and you'll get 0. So I will leave that to you to do the algebra. It's not bad. You should do the algebra. Let's do a more enlightening proof. If x and y are independent, what is true about x minus mu x and y? Independent. Right? I've just shifted all the values of x. Does everyone agree? It would be amazing if all of a sudden I know, oh, I know what x minus mu x is because I know what y is. Well, then I would know what x is. I could just add. So do we agree that x minus mu x and y are independent? Okay. Now, what do we do? Now we know x minus mu x and y minus mu y are independent. Now since they're independent, the expected value of the product is the product of the expected values. So now we get that it equals the expected value of x minus mu x expected value of y minus mu y. I actually much prefer this proof in terms of what's going on, because it gives you this added fact that if x and y are independent, so does x minus mu x and y minus mu y. You have actually possibly seen something like this years ago. You might have seen, how many of you remember the mean value theorem? You might have seen the special case of the mean value theorem where you first assume that f of a and f of b is 0, and then you show, if you know the mean value theorem, this is called, whose theorem? Whose theorem? It's Rolle's theorem, who was actually concerned that calculus was not on firm foundations and now is only remembered for a calculus result. History can be interesting. So Rolle's theorem is, if f of a equals f of b, then at some point, if your function is differentiable, f prime of c is 0. You can then use that to prove the mean value theorem in general, that there's some point where your instantaneous speed is your average speed. We are essentially doing something similar here. We're passing to easier cases. We know the case when x and y are independent, that the expected value of a product is the product of the expected values. So rather than doing the algebra, we can actually just look at a better choice of random variables. Okay, any questions about this? All right, so the next part that we want to start to do is we want to start working a little bit with variances. How many of you have done covariances and correlations? All right, so a good number of you have. I am not going to do too much with covariances and correlations in this class. We will either assume that the variables are independent and life is good, or we will assume that they are dependent and life is bad and we will give up in frustration. And I will just leave that for the other stats classes. There will be a few times towards the end of the semester I like to save some time to talk about research I've done with students. And one of the problems we might talk about in additive number theory combinatorics involves a situation where we have to deal with the correlations and the covariances. And in fact, what's fortunate is we don't have to calculate them exactly. We just have to get a rough estimate. All right. So the following is a big theorem. Let's say you have x is a1 x1 plus an xn. Then the expected value of x is equal to the sum of ai expected value of xi. And if independent, the variance of x is the sum of ai squared variance of xi. As I was writing this, I almost forgot to square the ai, and I caught myself in time. I don't think you noticed. Did anybody notice? I know some people noticed the subliminal message in Wednesday's class. If you hit pause around 2:09, 2:10 in the video, you will see the subliminal message. Why do I know it can't just be ai? As I was writing it, I realized it can't just be ai. Yes?
Because you can cancel each other out.
Yeah, if I imagine that all the a's are negative, I can then have my variance as a negative quantity, and variance can't be negative, right? You know, the variance of x, recall, is the integral from minus infinity to infinity of x minus mu of x squared times the density dx. Well, that's always greater than or equal to 0. So there's no way that the variance could just be the sum of the AIs. So it could be absolute values, which would be a nightmare. Fortunately, it's squares, which works out pretty well. All right. So let's start doing the algebra for the proof. We've already proven the first one. We're not going to prove the first one again. So let's look at the variance of x, which is going to be the expected value of a1 x1 plus an xn minus the mean of this, which is a1 mu x1 plus an mu xn, and then I square the whole thing. It's nice to have a large blackboard. All right. now we have to do some algebra. Right? This is my random variable. I'm subtracting off its mean. I'm squaring. This is how I calculate the variance. The variance is just this expected value. How should we attack the algebra? What should we do? Yes?
Group the AI terms.
Yeah, let's group things together. You know, if I've got an A1 x1 and an A1 mu of x1, let's group those together. And so you'll get A1 x1 minus mu1, and I'll put the A1 outside, plus dot dot dot, plus AN xn minus mu x1 mu xn, and I square the whole thing. So now when I square it, I'll get this term squared, plus this term squared, plus this term squared, plus this term squared, plus all the cross terms. Okay? And you can begin to see, that's where, here's the AI squared variance of xi. The square of this is going to give me A1 squared variance x1. So when I square it out, I get a lot of what I want. So when I square it, after some algebra, I will get the sum of AI squared variance of xi plus a sum I less than j, AI, AJ, expected value of xi minus mu xi, xj minus mu xj. And there's one small error in this line. Yes?
Don't you have the choose, like,
Yeah,
choose two?
so I actually have a factor of 2 over here.
Oh.
Because when I'm crossing terms, I could have, let's say I could have 3 and 4, and I could also have 4 and 3. So when I is not equal to j, there's 2 ways to get such a contribution. So I'm explicitly summing over all I less than j. I don't want to include I equals j because that term is handled differently. That's why I'm pulling those out, and those are the terms up here. And then the I less than j term, well, 3 less than 4, if I'm looking at my indices here, I can always assume the smaller term comes first, but it could have been written the other way, so I've got to double count. So it's just when you FOIL, you get the twice for the cross term. Now you can see why we want to assume independence. If independent, what is this equal to? 0. So this is 0 if independent. And that's the proof. Okay? So again, this is just an algebra, but the main idea is that if they're independent, the variance of a sum is the sum of the variances. Okay? One of the things you need to remember is there's a difference between a definition and a practical means of doing something. How many of you remember your multivariable calculus, your directional derivatives? The definition involves taking a limit, but then the formula to compute it is take the gradient and dot it with your vector. And from a computational point of view, this is how you calculate directional derivatives. You do not go back to the definition. So note, the variance of x is the expected value of x minus mu of x squared. But from a practical point of view, we frequently use this formula. And this is just an algebra exercise. Just expand the square, first outside, inside, last. You'll get expected value of x squared minus twice x mu x, and you get plus mu x squared. And then when the dust settles, oops. Oh, no, it is fine like that because this is just equal to the mean. This is a much more useful formula for the variance. It also allows you, because these two are equal, to deduce something that is not immediately clear. If I give you a random variable, is it possible that the expected value of its square is less than the expected value of itself squared? No. Because this expression is the variance, and what do we know about the variance? The variance is non-negative. So because we know the variance is non-negative, we know this has to be non-negative. It has to be, in fact, well, we'll say it has to be non-negative. It's not immediately clear when you just look at this that this would have to be non-negative. Maybe the square has a slightly different distribution and such that its expected value is less than the expected value of x squared. Can't be the case. There's a really interesting problem. It's called the Hamburger moment theorem, where if I give you a sequence of numbers, the question is there a random variable that has these as its moments? Or conversely, when I give you a sequence of moments, when does that uniquely determine your probability distribution? It is not always the case that a sequence of numbers determines a probability distribution, or if it determines one, it may not determine one uniquely. The real subject we need to figure out all of this is complex analysis. All right, so this is the theoretical part of today's lecture. Now it's time to look at applications of this. So we're going to start by looking at Bernoulli and binomial random variables. So I don't think we've explicitly used them too much in this class. We've implicitly used them. We've talked about indicator random variables once or twice. I want to just formally define them. And so we're going to start meeting more and more random variables and starting to see how good they are. And we're going to begin to see how our techniques allow us to bypass a lot of challenging calculations. I was talking with one student. I'm using him as a data point for the entire class. So based on my conversations with the student, I'm assuming most people have shaky at best memory of spherical coordinates and the resulting Jacobian change of variables, and that almost surely no one has seen the equations for spherical coordinates in n dimensions. In some of the problems we need to do later in the semester, we will actually need n-dimensional spherical coordinates unless we do a nice trick which allows us to bypass all of that. And so we will concentrate a lot on that trick. It's called integrating without integrating. It uses the fact that if I give you a probability distribution, what must its integral be? 1. So because of symmetry, you can often reduce to not needing to know what the random variables are and what the actual change of variables are. And we will see remarkable applications of this. We will actually calculate the volume and the surface area of the n-dimensional sphere without writing down the n-dimensional spherical coordinates by using a chi-squared random variable. So for those of you who've seen chi-squared random variables, raise your hand. This is a great application of chi-squared random variables. I know in your stats class you do other things with them. This class is jointly listed math and stats, so we'll do a few math theorems as well. All right. So the first thing over here is we have Bernoulli, and over here we have binomial. So for Bernoulli, we have a parameter p. For binomial, we have two parameters, n and p. And we say x is Bernoulli with parameter p if the probability x equals 1 is p and 0 is 1 minus p. And it's binomial, so we'll write x is binomial np if the probability x equals k is n choose k, p to the k, 1 minus p to the n minus k, for k in 0, 1, 2, ... n, and 0 otherwise. Okay? So these are two extremely common random variables. What is the first question you want to ask? What's your mean? Right? So let's calculate the mean of a Bernoulli. So the expected value of x, well, because it's discrete, I'm not going to do an integral. It's 1 with probability p plus 0 with probability 1 minus p. All right. So the mean of a Bernoulli random variable with parameter p is p. Okay? What's the next question we should ask? Variance. So the variance of x is I'm going to use the formula, it's the expected value of x squared minus the expected value of x squared. So what's the expected value of x squared? It's 1 squared with probability p plus 0 squared with probability 1 minus p, and then I subtract off p squared. So what's the variance equal to? P
squared.
And so I'm going to write that as p times 1 minus p. It is p minus p squared, but p times 1 minus p is a really nice way to write it. These are the two probabilities that emerge. The probability that it happens and the probability that it doesn't. If you think about it, it seems very reasonable that the variance should only depend on the product of p and 1 minus p. So whenever you see a math formula, you want to step back and see, is this reasonable? Because really, this is counting the probability that we get a success. I'm looking at things in a positive light. I'm looking at the probabilities of success and how many successes do I have. What could I look at instead if I was a not so happy, sunny disposition person? Say I rooted for teams other than the Red Sox this time of the year. Failures. So I could look at the distribution of failures. Okay? How are successes and failures related?
You don't succeed.
If you don't succeed, you fail. And so really, if y is the distribution of the number of failures, y is just 1 minus x. Right? So since y is 1 minus x, the variance of y should be essentially the same as the variance of x. This is an extremely important point. And so I want you to really drive it home. I'll drive it home, I guess, a little bit more with the binomial. But we just saw from our beautiful theorem here that the variance of a sum is the sum of the variances with the coefficient squared. So if I have a negative 1 just squares to 1. And if I shift everything by a constant, does it change the variance? Does it change the fluctuations? If I add $1,000 to everyone's bank account, does it change the fluctuations, the variance in your bank accounts? No. It changes your baseline, but it's not going to change your fluctuations. So that's why if we look at y is 1 minus x, then the variance of y is the same as the variance of x. But now, if p is the probability of success, the probability of failure is 1 minus p. So this is looking like, it's almost looking like a binomial with parameter 1 minus p. So this just gives you some intuition as to why the variance for a binomial, for Bernoulli, should involve p times 1 minus p. I shouldn't really be able to see a difference between those two. So whenever possible, if you can make symmetry arguments, it is tremendous what you can do. I'm trying to leave time today to do the Gaussian problem. I'll actually do a harder version of the Gaussian problem than I emailed you to show you the power of symmetry. All right, do we all agree that the Bernoulli calculation is not that bad? It's really takes on two values, 0 and 1. 1 squared is not that bad. 0 squared is not that bad. Let's look at binomial. So now x is binomial NP. Okay? So if x is binomial NP, the expected value of x is now going to be the sum, k goes from 0 to n, of k, and then the probability that x equals k, which is n choose k, p to the k, 1 minus p to the n minus k. And now you have to evaluate that sum. We will see later a trick to evaluate the sum. It's one of my favorite techniques in math. It's called differentiating identities. Right now, this looks painful. Your first thought is probably, well, n choose k is n factorial over k factorial, n minus k factorial. Maybe the k cancels down here a little bit. Maybe I pull out an n. Maybe there are some games I can play. And maybe you can get the algebra to work. It's possible. Happy to leave that to you as an exercise. I have no desire to make the algebra work. Right? We've spent all of this time listening to linearity of expectation is great. We should start to see some dividends. So you can view a Bernoulli random variable as the building block of a binomial. So we can say x is equal to x1 2 plus xn, each xi is a Bernoulli with parameter p. So if I'm doing something n times, and I want to count, I'm flipping a fair coin n times, and I want to count how many heads I have, that's exactly what this is. So let me just move this back. So if I want to flip a fair coin n times, and I want to count how many times I have exactly k heads, that's exactly what this is. I choose k out of my n things to be heads. The probability that each one of those is heads is p. The probability that everything else is a failure is 1 minus p, and I get the following. I can view this, however, as a sequence of n independent trials, and each trial is the same. And now, if I want to calculate the expected value of x, this is just the sum, I equals 1 to n, of the expected value of xi. Well, what's the expected value of each xi? It's just p. We have n of them, so we get np. And again, if you think about this, this is quite reasonable. I have a probability p of success. I do something n times. How many successes do you expect there to be? N times p. If I wanted to calculate the variance, this is where it's nice to be the professor at the blackboard. I replace the letter e with variance, and I'll end up having this, and then I'll subtract off np squared. And so now I get to do the sum with a k squared. So if the previous algebra seemed inviting to you, I encourage you to delve even deeper and try to do this one by brute force. There's ways to do it, and we will see later in the semester ways to do that algebra, but not by brute force, by a clever backdoor trick called differentiating identities. The variance of x, by what we just did before, is the sum, I goes from 1 to n, of the variance of xi. And each xi has variance p1 minus p, so when the dust settles, you get n p1 minus p. Now, one interesting consequence of this is you can actually use this to now prove a theorem about this. Because we know this, we now actually know what the sum is. So here is a way to calculate sums of binomial coefficients. Interpret them as probability problems. Okay, so this is our first real big dividend of linearity of expectation. If we want to ask the big questions to the binomial distribution, what's your mean? What's your variance? To do it by brute force is painful. To do it with linearity of expectation is trivial. You reduce the problem to almost the simplest possible random variable you can have. It's 1p of the time and 1 minus p of the time. There's only one thing simpler. What's the only thing that's simpler? What uniform? Very specific uniform. Uniform discrete with how many elements? More than finite. How many elements? One element. That's the only thing you'll get that's easier than this. If I tell you it's always this value, no matter what you tell me as your input, I always give you the same value back. With a 100% chance, you will always get the following result. That is a very easy random variable to analyze. If you always return the value c, what's your mean? It's c. What's your variance? Variance is 0. All right. So let's do the symmetry problem next. So I'm going to make the problem a little bit harder than I emailed you. So x and y are normal 0, 1 random variables. So n mu sigma squared means your density is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. This is the normal distribution with mean mu and variance sigma squared, or standard deviation sigma. Okay, we have not done this in this class. How many of you have seen this before? How many of you have not seen this? Okay, so that's perfectly fine. We will prove why this works. This is an example of notation, right? Because I'm writing mu here, what do you think mu represents? The mean. And what do you think sigma squared represents? The variance. You have to prove that this does have mean mu, and you have to prove that this does have variance sigma squared. But if I am writing it like this, it better be that case. If not, this is horrible notation here. A normal has two parameters. And by writing it like this, things are nice. So here's the question. What is the probability that x is greater than, I'll do y cubed plus y. This is a little bit harder than the problem I gave you. The problem I gave you was, what's the probability that x is greater than 3 times y? Well, what we could do is we could do the following. I integrate, y goes from minus infinity to infinity, and then I integrate, x goes from y cubed plus y to infinity, and then I put in the densities. So you often use eta for the normal density? I'll put it in explicit. So I have 1 over square root of 2 pi e to the negative y squared over 2, 1 over square root of 2 pi e to the negative x squared over 2, and then I would integrate dx dy. So this is the integral you would need to do. This is an extremely bad integral to do because we actually don't have a closed form antiderivative of the Gaussian density. Yes?
Where does these functions come from?
This is just the density. I'm assuming x and y are normal with mean 0, variance 1. So just mu becomes 0, sigma becomes 1. This would be the integral of the probability that x is greater than y. So if you think back to the baseball problem we did on Wednesday, we were trying to calculate what's the probability that this random variable is greater than this random variable. So we've seen calculations like this before. This is an unpleasant integral to do. Does anybody know what the answer is to this integral? So the hint is, it's a symmetry argument, so the answer has to be elegant. It has to be a nice number. Yes?
Can we write 2 times that eta because they follow the same PDF?
I'm sorry?
So like x and y are the same PDF.
Right.
So
But we're evaluating them at x and y. We're evaluating them at different points. Right? So we have to do this integral.
Is it half?
It's a half. When I'm saying it by symmetry, it's got to be something nice. So the key thing to note is we have x here, and I can write this as y times y squared plus 1. Y squared plus 1 is never negative. So x and y both have a 50-50 chance of being positive and a 50-50 chance of being negative. I'm only going to say a few words. I will let you write things down rigorously. I will let you use the CBF. If x is positive and y is negative, is x going to be greater than y cubed plus y? Yes or no? Yes, always, automatically, has to win. If x is negative and y is positive, will it ever be greater? So these two cases perfectly cancel out. If x and y are both positive, or x and y are both negative, let's say you take the same value of x and y. Say maybe you take x equals 1 and y equals 4. The probability of the pair 1, 4 is the same as the probability of the pair 4, 1. And when you do it 1, 4, the y's win. When you do it 4, 1, sorry. What I want you to know, right. When I do 1, 4, and I do negative 1, negative 4, that's the way I want to do it. If I do 1, 4, 1 is not going to be less than 4 cubed plus 4. But when I put in negative 1 will be greater than negative 4 cubed minus 4. So with these two pairs, it's always going to be the case that one of them wins for x and one of them wins for y. And so these will perfectly balance. So because everything balances, what's the probability has to be? 1/2. So you don't have to do the double integral. Questions like this, if you are ever doing quant job interviews, expect stuff like this. If you write something down as, oh, it's a really messy integral, you may be able to argue that you are on pace to get the right answer, but it is unlikely you will be able to get the integral evaluated in the time that you have. If there's time at the end of the class today, I will talk about a dispute I had on whether or not an integral was doable with an interviewer when I was in your shoes many, many years ago. Frequently, these problems have clever answers, trick answers. There's a symmetry going on. And so whenever you have a problem, if you can, spend a moment and try to think, is there a symmetry? If somebody asks you a question in an interview, say, that's a really good question. Can I have a second to collect my thoughts? Do not feel compelled to start doing your first instinct. Your first instinct might be, oh, well, I can just write down the double integral. Almost surely the double integral will not work in the amount of time that you have. All right. So the last thing for today, and this is going to be one of our key ingredients in our march to the central limit theorem, is convolutions. So the idea is we want to take random variables and we want to create new random variables. So z will be x plus y. And the question is, what is the density of z as a function of the densities of x and y? Is there a nice formula? Well, let's calculate the probability that z is less than or equal to little z. So this is the cumulative distribution function of z. So this is going to be the integral x goes from minus infinity to infinity, integral y goes from minus infinity to infinity. Then I'm going to fix the bounds in a second. Well, no, I'll fix it right now. Given a value of x, if I want x plus y to equal z, little z, how large can y be? So what's the largest y can be if I want x plus y to equal z? Z minus x. And so if I want it to be less than or equal to z, y can go all the way up to z minus x. And so I've got the density of x, the density of y, dy dx. Yes?
Can't x only go up to z?
No, because I have x plus y. So if y is allowed to be negative, I can have it pull it down. If y is not allowed to be negative, then this would actually take on 0 for negative values of y, and then that would force x to stop at z. So this is where we're going to do pure mathematics. This is the cumulative distribution function. Its derivative is the density of z. Well, let me do the y integral. So I'm going to have the integral x goes from minus infinity to infinity, the density of x. And now, when I do the y integral, I just get the cumulative distribution function of y at z minus x minus the cumulative distribution function of y at negative infinity. What's wonderful is I don't need to know exactly what that cumulative distribution function is. There's just some function. It's the antiderivative. So I evaluate the antiderivative at z minus x, and I subtract off the antiderivative at negative infinity. What's the cumulative distribution function at negative infinity? 0. All right, so this part goes away. And so now I get that my cumulative distribution function of z is the integral x goes from minus infinity to infinity of fx of x, big Fy of z minus x dx. I want to take the derivative. What's the derivative of the integral? You wave your magic wand. What's the derivative of the integral? I'm sorry?
Just the slope?
No. I have the order of operations. I have a derivative and an integral. See how the only z dependence is inside the integral? I would love to pass the derivative through the integral. So you take a class like real analysis that justifies when you can shove the derivative inside the integral. And once we do that, what's the derivative of the function that's the antiderivative of little f of y? It's just little f of y. So it's interesting. We integrate the function temporarily to get big F of y, and then we immediately differentiate it and get back down to little f. So nowhere in the analysis do we ever have to use the cumulative distribution function of y. So we use d by dz of the integral is the integral of d by dz, and we now get that the density function of z is the integral x goes from minus infinity to infinity fx of x, and then we get fy of z minus x dx. And if you think about this, this is a really natural formula to get. What's the probability that x plus y equals z? Well, if x equals x, then y has to be z minus x. I multiply their probabilities, and I go through. I did not write a key word on the board. There is a key word that I need to use here. What am I assuming about x and y? Yes? They're independent. So I do need x and y are independent. Okay? So as an exercise, where did I use x and y being independent? So I will leave that as an exercise for you. It was used. Try to find it. So we will write as notation fz is fx star fy, and this is called the convolution. So it takes two functions and it convolves them and it gives you a new function. So we now have a new operation. We have the star operation. You can ask questions about this operation. What's one question you might want to ask about it? No, you can't ask what its mean is. What might you want to know about this operation? What kind of properties might you want? Yes? Does it commute? And so the answer is yes. You can show that it commutes by doing a change of variables. That's the algebra proof. The high level proof is this is the density of x plus y. This is the density of y plus x. Because addition is commutative, this inherits commutativity. Okay? This is the higher level proof. I like this proof more than the algebra proof. So we know it commutes. What's the next thing you might want to know about it? You have to remember all these different things. If you're taking group theory, what's the next thing you might ask? Yes?
Is it identity or inverses?
Before identity or inverse, there's something easier. Yes? Is it associative? And it turns out, yes, it's associative. So fx star fy star fz is fx star fy star fz. It is associative. Now you can ask about identity and inverses. Inverses is going to be very hard. There is an identity element. The identity element is basically the Dirac delta functional. It's not really a function. It's 0 everywhere, but at 0 where its value is plus infinity. You can think of it as a limit of, say, Gaussians with variance getting smaller and smaller and smaller. Another way you can look at it is the integral from minus infinity to infinity of f of x delta of x dx is just f of 0. It just returns the value of your function at 0. Later in the semester, we might talk a little bit more about this. But this is a way to try to make this, it's not going to be a group. Anybody know what this is called? I had to look it up. It's a commutative subgroup with identity, and that is known as it's a monoid. So it's really close to being a group. But you do not necessarily have inverses. And that makes things problematic. We will see this later in the semester. What is the big theorem we are leading up to? The central limit theorem. The central limit theorem deals with sums of independent random variables. This just told us how to get a density for a sum in terms of the constituents. The density of the sum, it's the convolution of the densities. And so, as if we have identically distributed random variables, we just keep convolving. All right, this is a good place to stop.